after understanding what an heat engine was and how we calculated the efficiency of a heat engine, the next small concept is the Carnot refrigerator or the refrigerator, right. So, the refrigerator is functioning just in the opposite way as the heat engine was functioning. So, in a refrigerator, what is actually happening is that it is pumping out heat. So, it's a very common thing that we use. So, in a refrigerator, we want to keep things cool. Okay, so how do we keep things cool? We have to try to bring heat out of the system. Okay, so say you have a system in here and you want to bring heat out of this. So how are you going to do that? So if you do work on the system, so you're doing work on the system, that means you are compressing the gas that is inside it. Okay, so you're compressing the gas inside it. So when you're compressing, the work done, the sign of the work is negative. So basically this becomes negative. So when this work becomes negative, now when this work becomes negative, so you're increasing the energy, like you can think like that. When you're compressing it, you're increasing the energy. So what that will do, because of this, it will try to repel heat out of the system. So when you did the work on the system, this will try to bring heat out. So the instrument that is pumping heat out is called a heat pump or a refrigerator. Okay. So the concept is very similar to what we were studying in the case of the heat engine. This is just the opposite of what it is doing. Okay. So in the case of heat engine, we were getting heat we were getting a Q hot heat inside, and in response to that heat it was expanding. But in here, what you're doing, you're compressing the gas, and in response to the compression, heat is being pulled out of the system, pumped out of the system. So that is a function of a refrigerator. Now, as we saw that the efficiency of the heat engine was measured, and you measured it in terms of the eta, which was TH minus TC divided by the TH, right? So that was how you were measuring the efficiency of the heat engine. For the heat pump, this is how you measure the efficiency. So this is called the coefficient of performance. So beta is called the coefficient of performance. So if you want to actually quantify how well a refrigerator is functioning, you have to take use of this, the coefficient of performance. So this is a real quantity. Okay, so this is a real quantity. Okay, this is not a hypothetical case. This is a real quantity that you are going to measure. And in here, so in the case of the heat engine, you saw that the Q was towards the QH was in the denominator, and the work that was the amount of work that you were getting was in the numerator. Why? Because in the case of the heat engine, what you were doing, you were giving in heat. So what you were supplying was the heat. So you were supplying heat, and what the machine or what the instrument was supplying back was basically the work. But in this case, the case is reversed, right? So in this case, you are doing work. So this is basically the input. So this is the W is the amount of work that you are doing. So this is the input, okay? And the QC is the heat ejected out. So this, therefore, the amount of heat ejected out by the system is the output, right? And this W was the input. We can also understand in this way that W is the amount of work needed to remove the heat. So what you're doing, you are doing work in order to remove the heat, but this is the input, and that is why this is in the denominator. Okay, so this is what you are providing, and the numerator is what you're getting back. Okay, So why this negative sign? Okay, so since we said that the QC is the heat ejected out, and when heat is ejected out, Q becomes negative, right? So to make this quantity beta, the coefficient of performance, a positive number, we have supplied the minus in order to cancel out the minus that is coming out of this QC, because QC is exothermic, is in itself negative. So to make this quantity positive, we are supplying a negative sign on top of that. Okay, so this is basically the coefficient of performance of any real instrument. Now, like we calculated the efficiency of the Carnot cycle, which was a completely hypothetical best case scenario, we also try to find out the best case scenario for the refrigerator, and that refrigerator is called the Carnot refrigerator. Okay, so this is how you calculate the efficiency of the Carnot refrigerator. So this is hypothetical. This is a best case scenario. Why? Because we saw that in Carnot cycle in heat engine, we derived the beta Carnot as one of the eta Carnot. The efficiency of the Carnot cycle that we did was a hypothetical notion, and we can use the same hypothetical scenario and you just reverse the process and you'll come up with this value in which you have the temperature of the cold system, and over in the denominator you have the temperature of the hot minus temperature of the cold. Okay, so this is a hypothetical case and this is the real case. So this is how you calculate the efficiency of a refrigerator and a Carnot refrigerator. Now, using the concept of the Carnot refrigerator, what we can do is we can come up with the explanation of why absolute zero, which is 0 Kelvin, cannot be achieved. Okay, so let's try and do that. Now, we saw that beta Carnot is Tc over Th minus Tc. Okay, so imagine that you are trying to build a refrigerator that is pumping out heat from the system in order to make the system, the Tc, the final temperature of the cold system. You want that temperature to be 0 Kelvin. So let's assume that you are trying to make that, and we are trying to calculate how much work do we need to do in order to do that. Okay, so because in order to remove this heat, you need to do some work. So what is the amount of heat needed out? We understand that in terms of the Tc. So we want the Tc to be 0 Kelvin. Okay, so we want this to be 0 Kelvin. So what should be the coefficient of performance of the beta Carnot, which the hypothetical refrigerator? This becomes 0 over Tc, which is 0. So your beta becomes 0. Okay, I'll just get these numbers. So this is 47, this becomes 48. Okay. Oh, all right. So since we now know that the beta Carnot that is needed to get to an absolute 0 temperature in a refrigerator is 0. Now we want to find out what's the amount of work do we need to do in order to achieve that. So from here, from that equation number 47, so we got this from equation number 48, and we are using equation 47 to find out the amount of work that you need. So if you rearrange this, the amount of work that you need is this much. Now you know, beta. So we know the beta in here is 0, so this quantity becomes undefined or infinity. What that means is, in order to get to 0 Kelvin temperatures, the amount of work that you need to do on the refrigerator, on the system, to get to 0 Kelvin is infinity, right? So you have to do infinite amount of work on this refrigerator, on this gas, on this system, to get to a temperature that will equate to 0 Kelvin. And since infinite amount of work is not possible, you cannot get to 0 Kelvin. And so that is the whole idea about the absolute zero. So we cannot do infinite amount of work, and that is why you cannot get to absolute zero. Okay?